All right, good morning. It's Physics Teachers Are Awesome, number 95. Let's see. This is, I think, a college class. I had noticed in the name of the playlist is a 4-digit number, which is often what colleges use, but unclear. Looks like some sort of centripetal acceleration problem. All right, let's make sure you can see my mouse.
Last example, problem involving centripetal acceleration. So a conical pendulum formed by attaching a 500-gram ball to a 1-meter long string. It moves in a horizontal circle that has a radius of 20 centimeters.
Ooh,
So
I like
20
that.
centimeters is the radius.
So right away we're noticing that they're using an image, my guess from the textbook or something, and then annotating it. I think that's really, really great. And from a setup perspective, I think this says Microsoft Whiteboard at the very, very top. So I've not used Microsoft Whiteboard before. So I'm curious. It looks like pen choices are right in front of you, and the thickness seems like a natural thickness. You know that I'm always trying to find one that would show my mouse a little bit better, so let's watch to see if we can see their mouse when they're moving it around. I love problems like this because it has the word pendulum in it, and so we think there's going to be pendulum-y type stuff in there, but honestly the thing just goes around in a circle. So it's fascinating when you realize that there's just, you have to figure out how much physics you want to bring to it. And so the questions are, what are the tension and the ball's angular speed in RPMs? Ooh, cool. So what do we know? Isn't that fascinating that there's no time-based information, time or speed-based information in the problem itself? And so, we're just the biggest thing is going to be the gravity is sort of, I was going to say driving this. Driving is probably the wrong problem. Because it's interesting, right? Because if you just hang something here, just put it right there, just let go, whoop, it would just come down and be a regular pendulum. So you got to do something. You have to basically instill part B into it, and then part A just comes along. If instead you put this here, and you put it there, and then you pulled it, whatever this tension is, you pulled it, and say, okay, well, I've achieved part A, now it must go in the circle. Well, if you let go, nope, it'll just, as soon as you let go, the tension's gone, it'll just be a pendulum again. So that's a really interesting problem.
Of this circle it moves in. Now, horizontal circle means this circle that's traced out in the picture is the same height from the floor at all moments in time.
Cool.
The picture they've given us is kind of down at an angle to get a picture of what's happening. The ball...
That's a great point. Oh, I love that.
Is tracing out a cone. So the ball itself traces out a cone. The circle, the string traces out a cone. If I were to look at this ball perfectly from the side, I would just see the edge of the circle. The radius would be there. The string would go up to...
A couple of comments quickly about the technology. So it doesn't look like we can see where the mouse is when they're not actually drawing, and that stinks. I'm not sure if there's a whiteboard that does it. I know that there's screen capture that'll do it, right? So independent of whatever software you're using to draw on, your screen capture tool can draw a circle around your mouse at all times. So anyways, that's just a little brief aside. But I wanted to point out something. Right as they were drawing this here, they kind of drew it here and then they erased it back down. The standard eraser in, let's say, OneNote would have just, boom, erased the whole line. So you touch the line with the eraser, bam, the whole line's gone. And there's times when you really need it to be more like a pencil eraser, right, where you just want to erase part of it. And so I'm not sure if that's how they have their set or if that's just the default in Microsoft Whiteboard, but interesting.
Here. So the string is held in place at the top. The point of support is what is labeled in the original picture. The string has a length of 1 meter. The radius it makes is 20 centimeters, so 0.2 meters.
Nice.
We know there's an acceleration that points towards the center of the circle.
Love it.
So depending upon where the ball is, towards the center of the circle is varying. My picture, this side view, I'm choosing the moment in time when the ball is at the far right in my view.
Love it.
At that moment in time, I know the tension points up and to the left towards the point of support. I know the force of gravity points straight downwards. The acceleration, the centripetal acceleration, points to the left at this moment.
Cool.
So this tension force has an X component and a Y component. When we think about the net force needing to equal MA, in the radial direction specific.
Just wanted to comment on what she just did. She put arrows over these things. So someone on Twitter, I don't know, a week or so ago asked the question, which would we rather see in textbooks, bold or arrows over the top? And at the time I checked, it was one of these Twitter quizzes. At the time I voted, the dominant vote was for putting arrows over it. That's the same thing I voted for, and the reason was because that's what students can do in their notes. Bold is actually hard to do with your handwriting. And so I thought it's really interesting that even as a brief aside over here, she still did it, or they still did it. And so that's really, really interesting. A couple of points, right? So the color went from green for this to blue, but I think that she's been they're being very, very clear about, who's doing what. And I was thinking as they drew these component vectors of the tension, for me, when I first learned this stuff, that's when I had the aha moment. It's like, oh, I get it. Bam, done. I can see, yep, all right, this is going to lead to this, which is going to lead, I know these angles, and so I know what this is. I know what this is, bam, I'm done. I got the whole thing figured out. And so it's interesting to think about when students have that aha moment, like, okay, it's all there. The rest is just cranking, some math. And so we don't know where our students are going to get to that point. Some might not get there in this particular approach. But it's interesting. I wonder how we would respond if you posted a video like this and asked the students, at what point did it become just a math problem? Or at what point did it become, math is the wrong word, an algebra problem, like a turn the crank, an arithmetic problem, right? At what point was it like, oh, I get it. And so for me, it literally would have been, when I was a student, when these two were drawn, and I would have realized how to slap this problem together. So I do wonder if any of you do that, track or ask your students to say sort of the minute marker time when sort of it clicks.
It's the X component of tension that points to the left. So that has to be what is creating the centripetal acceleration. So the X component of tension needs to equal mass times the centripetal acceleration. The Y direction, up and down, well, the problem tells us that the mass is moving in a horizontal circle.
Love it.
Meaning it's not moving up or down.
Love it.
So that Y component of tension is balancing out gravity perfectly.
That's cool.
There's no acceleration in that.
So I just want to pause and talk about negative signs here, right? So there's not a single negative sign on the screen at all. And so I think that the idea that this is equal to mg and that this is mg, really they're fighting against each other, but it was really, really great how they used their vocabulary words to make that clear, right? Like, oh, they're balancing each other, so it must be this. I think that a lot of times people will say, man, I have to tell them which direction positive y is, and so let's say positive y is up. Oh, shoot, I should have put a negative sign here. But that would have made the way that they described this to be a little bit more clumsy. So I really, really liked how this goes, though I also recognize that helping students understand exactly where the negative signs go, if you need them for the calculation, is really, really important.
Vertical direction. Now we do have M, we do have G. We're looking for tension in the string, the ball's angular speed. So to talk about tension having X and Y components, we need an angle of some sort. So if I call the angle with the horizontal theta, I know the angle that tension makes with the horizontal is the same as the angle the string makes with the horizontal.
Oh, that was
the
great.
tension vector is directed along the length of the string.
Wow, that was actually really, really, really cool, right? There's two different representations here that have the exact same angle. This is a drawing of the string. This is a force diagram. And so I'll be honest with you, as soon as they drew this theta, I was done. I was like, yep, 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 yep. And then they put this theta over here, and I thought, oh, that's a little redundant. But it's like, whoa, mind blown. Like, multiple representations, we have to make sure the students understand that it's two different representations. They happen to share a very, very common thing, frankly, the shape of this triangle. But the units are completely different. These are lengths, these are forces. And so I thought that was really cool.
I have enough information in here to figure out what this angle is. And it's not sine. I know the adjacent side is 0.2. I know the hypotenuse. So the cosine of theta will be 0.2 over 1. So inverse cosine gives me an angle of 78.46 degrees.
Cool. So I think this might be somewhat drawn to scale here.
So I know this angle in here. The x component then of the tension is going to be t cosine of this angle. The y component will be t sine of this angle.
Cool.
Now, in terms of centripetal acceleration, we can substitute in either v squared over r or r omega squared. In terms of choosing, I'm going to look at what I'm being asked for. Since the problem is asking for angular speed, I'm going to plug in the r omega squared.
You know, it's really, really interesting. If this wasn't there, this in RPM, this absolutely, and then you're done, right? You can say, oh, okay, bam, I can solve for t, jam the t over there. I know m, I know r, I'll get omega all done. And it's kind of interesting that right at the last minute, they're going to have to switch over to RPMs. And so I guess what I wonder about is the value of breaking this last little thing into a part C, right? Like, you know, here's some equations that you're working with. This is all of the represents all the physics we've been learning. You should be able to get this. But of course, the reason why we ask about things like this is that some students have some experience with this. It's the, you know, units on the tachometer in their car, but we're not going to get anything near the thousands that you get in your car. So I'm curious what others think about this. And you know, they're just solving this problem that clearly came from the textbook. My question is a question for the textbook author, right? Like, should this have been a part C? Because just what's written on the screen right now is only going to get us to omega, and it's not going to get us to there. So I'm just curious what people think about that. I think I'm going to pause right here. There's a number of things that I really, really liked about this. I really liked making sure that all of the representations were connected. I liked taking some time to explain the drawing. That was really, really cool. All right, everybody. Well, I hope you have a great day. And remember, physics teachers are awesome.